Hello and welcome to my YouTube channel. Today we are going to talk about potential energy well and EK diagram. If you have not seen the previous video or previous lecture, then do visit the previous lecture before going through this presentation. So let's start the video. So first of all, let us talk about the basic definition of potential energy of hydrogen atom, and then we will come to the topic why it is called potential energy well, why it is called a well. Okay, now if you go through the previous video or previous lecture, you can see we have derived the potential energy of hydrogen atom. And we derived that potential energy is given by capital V, which is equal to the multiplication of E and minus E divided by the distance R, which is equal to minus of E square upon R. So now, in the CGS system, that is centimeter gram second system, same potential can be written as V equal to minus E square upon 4 pi epsilon absolute value of R or mod of R. Now, if you carefully observe, the first term E is the charge of electron. It is a constant value. 4 pi is a constant value. Epsilon naught is constant value. Only thing that is variable is R. Okay, so if we keep on changing the value of R, we may get different values of V, and that is also discrete. You cannot go for any random value. So if we substitute these values for different values of R, we will get different values of voltage or potential energy. So potential well does not have any sharply defined walls. So it is not a sharply defined wall, rather it is a continuous shape. I will come to that. The potential is only a function of radial distance R. Yes, it is only a function of R. So we can say potential V is inversely proportional to R. Rest of the parameters are all constant. All these parameters are constant. Now let us go deeper into the topic. So now why it is called potential energy well? Why it is not called just potential energy? For that, we have to understand this particular diagram. If you keep changing the value of R and try to plot that, then you will end up with this particular diagram, which is called the potential energy well of hydrogen atom, where you have the nucleus here, and if you move far from the nucleus, that means if you are moving up, okay, you are moving far from the nucleus. As you move away from the nucleus, the energy of electrons at different shells will have different values. For example, 1s will have energy E1, 2s will have energy E2, 2p will have energy E3, and 3s will have energy E4. So maximum you can reach up to 0, V equal to 0. And that is also explained in this diagram. Okay. So here you can see E1, E2, E3, E4 and so on. You can reach up to infinity. So if the more you go upward or towards the outer orbit, the more the energy will be associated with the electrons. And if you see this shape, it looks like a well. So if you take this shape to consideration, it looks like more or less like a well. And that is why it is called potential energy well. Remember, this is not a two-dimensional diagram. It is a three-dimensional diagram. For more information, okay, you can visit some of the websites which I will provide in the link. Okay, before that, let us talk about how can we get this particular diagram. Okay, for that you can take or you can use the link provided here. Okay, and just let me show you. If you go to this link, you will end up with a calculator in which you can put your functions, and based on that function you can draw the behavior of that equation. For example, minus e square. So for example, if you want keyboard, you can take the help of the keyboard also. Okay, divided by 4, and then if you need pi, 4 pi multiplied by, I am just skipping the epsilon naught because it is also a constant value. Instead of that, if I go for absolute value of variable x, if we plot that, just a second, minus e square, wait a second, here if I put minus, okay, if I plot it, still it is giving me an error. Let me just draw the equation. So here you can see, if I plot this function, I will end up with behavior which is shown in the graph. And if you correlate, then it is similar to that of the potential energy well of the hydrogen atom. So if you keep changing the value of x, you will get different values of energies or potential across the well. And remember, this well is not 2-dimensional, it is a 3-dimensional. So it is just like a cone. Okay. So let us continue with the presentation. Now, let us correlate this potential well with the 1D lattice. That means if we keep on adding the atoms, or if we keep placing the atoms adjacent to each other, how this potential well will look like. So let us first go through the 1D lattice, and then we will go for more complex lattices. So suppose you have 4 atoms as shown in the presentation. Then in that case, each of these atom will have its own energy well. Remember, here you have the nucleus on top. Okay, so if suppose they are having a distance d, or they are kept apart by a distance d, in that case the energy well will look like this. Okay, so you have these functions which are nothing but the energy wells for different atoms. And if I correlate that with the shells, then 1s, 2s, 2p, 3s. Do please visit the previous video so that you can understand why these distances are decreasing as we move towards higher energy shells. I have explained it in the previous lecture. Apart from that, we can see, or we can correlate that with the number n equal to 1, E1 energy, then E2 energy, E3 energy, E4 energy. We have discussed these energy or potentials in a detailed manner in the previous video. So here you have the free state, which is vacuum state, and at the bottom you have the ground state of hydrogen atom. So now, if we want to have more detail about these energy wells, then in that case you can take the help of this link, where you can have more detailed analysis of the energy well. So energy well, you can see here on the right bottom, this is our energy well. Okay, so you please go through the website. You will get a very detailed information about the energy wells of hydrogen atom. So here you have the energy well, for which we have the equation given by minus q square upon 4 pi epsilon r. Okay, if you keep on changing R, you will get different values of energy. Now let us continue with the presentation. Okay, these diagrams lead to a new diagram called EK diagram, or we can call it energy versus wave number. So in the previous lecture, again we have discussed about why it is called wave. Here we are going to present why it is called wave. Okay, and EK diagram is also known as Kronig-Penny model. So you can call it EK diagram, that is energy versus wave number, or also you may call it Kronig-Penny model, because these are the scientists who came up with this model. So what is in this model? In this model, you have wave number, which is represented by pi by a, 2 pi by a, 3 pi by a, 4 pi by a, and a is nothing but the distance between the two atoms. So suppose we have the same 1D lattice with 4 atoms separated apart by a distance a, and if you want to plot the energy in the y-axis with respect to the distance in the x-axis, okay, then in that case we may end up with something like this. And if we correlate that with the shells 1s, 2s, 2p, 3s, or energy associated to with these shells E1, E2, E3 and E4, then this diagram is called Kronig-Penny model or EK diagram. Now, one more fascinating thing about this diagram is that if you try to simplify this diagram, of course you may end up with something like this, where you can simplify this diagram in a very simplified manner that it looks like almost a square wave, or it may be represented by a square wave where you have higher and lower potentials. Or further, if you want to simplify it, you may represent that with a behavior which almost looks like a sine. Therefore, it is called wave function or wave number. So simplified diagram from the energy well, we can end up with something like a function of energy which is something like the wave itself, which is almost looking like sine wave. Remember, this is simplification of the energy model or energy well. So if we keep on adding the lattices, you may end up with multiple such energy wells, which may be aligned or may not be aligned. What does that mean? It means the lowest energy of one atom may align with the highest energy of the other atom, or vice versa. It may be aligned or may not be aligned. Remember, this concept will be used to design LEDs or light emitting diodes in the upcoming lectures. So remember, if we keep on arranging these lattices, we may end up with the energy wells where we may have aligned energy wells or unaligned energy wells. Let us continue with the present scenario. So here we call this arrangement periodic zone representation, where these atoms are assumed to be arranged in a periodic manner in the lattice, which forms the semiconductor devices or any other solid device. Based on these behaviors, we end up with the behavior of the energy or the energy band of such devices. Again, we are coming back to the correlation that we have here, the upper band, which is called conduction band. Here the lower band is called valence band. That means electrons from this lower band will go to the conduction band, and I will explain it in the upcoming lectures. But let us keep ourselves restricted right now to the EK diagram only. So now here we have in the y-axis the energy, the x-axis wave number, and in between that we have valence band and conduction band. Now further, if we just focus on the energy which is associated with the 0, then we can just focus on one of the wells which are aligned to each other, in that case, the well will look like this. Okay, we have in the upper side we have the conduction band, in the lower side we have the valence band. Remember, valence band are those band or those energies band where you have excess of electrons or which are filled with electrons. Conduction band, like we discussed in the previous lecture, might be totally empty or partially filled with electrons. Very few electrons will be there in the conduction band. In general, we do not have electrons in the conduction band. Very few electrons will be there compared to that of valence band. So, same diagram can be extended for a lattice, and it may be called extended zone representation, where you keep on arranging these lattices and get the energy versus wave number diagram or EK diagram for extended zone of multiple arrays of lattices, and that may look like something like this. So you have energy wells which may be aligned or may not be aligned, and these are very simplified diagrams of the EK diagram. So please go through this presentation, correlate this presentation with the previous lecture to have more insight about the energy diagram and the energy associated with hydrogen atom, and if they are having a lattice or array of atoms, how the energy will be distributed. With this, I would like to end this presentation. If you have any doubts or suggestion, then please share your doubt and suggestions or comments in the comment section. If you have not subscribed the channel, then please do subscribe the channel and share this channel with your friends. Thank you and have a nice day.